By assembling enough dominoes into just the right sequence, we can create a structure out of those dominoes that acts as a computer circuit, representing numbers, calculating sums, and ultimately performing any computation we'd like. So how does this work? Well, computers are powered by electricity. So if we replace a current flowing through a wire with dominoes falling along a path, we can model that idea. We'll represent a 0, or the absence of electricity, with a standing domino, and we'll represent a 1, the presence of electricity, by toppling a domino and starting a chain reaction. Ultimately, though, computers need logic, some system to convert inputs to outputs. And computer circuits consist of logic gates, small electronic units that perform some simple logical functions. One of the simplest logic gates is the OR gate. It has 2 binary inputs, and if both inputs are 0, then the output is 0. But if the first or second input is a 1, or both are 1s, then the output is a 1. In domino terms, this means we have 2 domino inputs, and we want the output to fall if either input is pushed. This is straightforward enough to create if we connect both inputs to the same output. If no input is pushed, the output is 0, and if either one of the inputs is pushed, the output is 1. And if both inputs are pushed, the output is still a 1. Our job gets a little trickier when we need to create what's known as an exclusive OR gate. An exclusive OR gate also takes 2 inputs, and produces a 1 as output when either the first or the second input is a 1. The difference is that with exclusive OR, the 2 inputs are mutually exclusive. In other words, if both inputs are 1, then the 2 inputs need to cancel out somehow, and produce a 0 instead of a 1. To build that in dominoes, we can have the 2 inputs cross paths with each other in such a way that they'll collide if both are pushed. If only one input is pushed, the dominoes travel around the corresponding curve, and the output is a 1, as it should be. But if both inputs are pushed, the 2 paths collide with each other and stop in the middle. As a result, the output falls over when either one of the inputs is pushed, but does not fall over when both inputs are pushed. One final gate that will prove useful to us is the AND gate. The AND gate takes 2 inputs and produces a 1 only when both inputs are a 1. Representing that kind of computation with dominoes feels tricky though. How could we design a domino output that falls only when both inputs also fall? Here though, we can again take advantage of falling dominoes' ability to halt the progress of other dominoes. We'll start with one input that has a relatively long path to the output. We'll then add an extra path coming out of that input that can interrupt the longer path, so to speak. If the input is pushed, then the shorter path of dominoes will interrupt the longer path of dominoes, and the output at the end won't fall over. And now, in order to create an AND gate, we just need to add a second input that interrupts the interrupting path. Watch what happens. If just the second input is pushed, nothing happens to the output. If just the first input is pushed, we've already seen what happens. The interrupting path blocks the longer path, and nothing happens to the output as well. But if instead we push over both inputs, then the second input interrupts the interrupting path, so the longer path of the first input can make its way to topple over the output. Now that we have the intuition for some logic gates at our disposal, we can combine them to perform computation. A half adder is a circuit that adds 2 bits. It takes 2 bits as input and produces 2 outputs, a 2's place and a 1's place. Adding 2 zeros and the output is a 0. Adding a 1 and a 0, regardless of order, gives us a 1. Adding 2 1s gives us 2, represented by a 1 in the 2's place and 0 in the 1's place. But notice the pattern here. The 2's place output is a 1 only if both inputs are 1s. That sounds like an AND gate. And the 1s place output is a 1 if either input is a 1, but not both. That sounds like an exclusive OR gate. So by combining the ideas from our domino AND and domino exclusive OR gates, we can create a domino half adder. If neither input is pushed, the output is a 0. If just one of the inputs is pushed, the 1s place output becomes a 1. If the other input is pushed, the 1s place output becomes a 1, and the input interrupts itself, stopping the 2s place from producing a 1 as well. And if both inputs are pushed, then they cancel out in the exclusive OR gate to prevent the 1s place from producing a 1, and nothing interrupts the pathway for the 2s place to produce a 1 instead. We've now built a very simple domino circuit that has the ability to add 2 bits together. And now to add bigger numbers, we just need to combine these pieces together. Putting 2 half adders together lets us build a full adder, which lets us add 3 bits together. The idea here is the same, but some of the domino paths need to be extended to be longer in the full adder. The length of each of these paths is important, since our domino logic depends on our ability to interrupt some longer path with a shorter path. If one of these 2 paths isn't long enough, we might not be able to interrupt it in time. The ability to add 3 bits together is actually all we'll need to be able to add any 2 binary numbers together. Binary addition, much like addition you might be familiar with in the world of decimal numbers, can be performed by repeatedly adding together 2 bits, one place value at a time, and sometimes needing to also add a carry bit from the previous step. So once we have a full adder that can add 3 bits together, 2 operand bits plus 1 carry bit, we just need to repeat that component over and over to be able to add numbers that are as big as we'd like. The resulting circuit requires quite a lot of dominoes, but the effect is pretty incredible to watch. A sequence of dominoes organized into logic gates, those logic gates compose to form half adders that combine to create full adders that, when put in sequence, can add any 2 binary numbers by very precisely determining which lines of dominoes should fall and which lines shouldn't. And ultimately, these are the same principles that govern what's happening inside of our computers as well, just with electricity as the force instead of gravity. Computer circuits combine to perform more and more sophisticated computations at speeds much faster than our dominoes can compute, of course, but using fundamentally the same logic.